Hello, good afternoon. We meet again. So in this session, we're going to talk about the autocorrelation function for AR2. Okay, so this is our ACF for autoregressive models with second order. Okay. So the specification of we're expecting to get AR models here, then the tails off gradually. Okay, so we're expecting the ACF will reduce, or it can be in an alternating way. Okay, so it will reduce gradually, okay, close to zero. So this is the ACF, this is the lag, okay? This is the lag. So this is what we're expecting. So AR1 also we have this tails off gradually. So AR2 basically will have similar result. Okay, so for the specification for AR2 models, so you have, let's say the series is xt, then you have the leg 1 of xt. Let's say this is phi 1. You have the second leg t minus 2, and then you have the series of the white noise. The zt is a random process with mean and constant variance sigma squared. So in order to there are many ways to find out the ACF. Okay, one of the way is using the Yarl-Walker formula. So Yarl-Walker formula will relate the covariance of the equation. So you have a covariance of X series. Okay, so let's say you have in terms of, so in general, this is the covariance of this is the leg tau minus 1 plus, so this is 1 and 2, so this is leg minus 2. So for any tau, sorry, any legs, okay, this is tau more than 2, okay, more than 2. So in order to find out the covariance of xt, okay, this series here, so the xt can be it can be price series, return series, or even volatility series. Okay, so now if you have a tau equal to 0, then we have 0 equal to phi 1. So minus 1, this is going to be minus 1. This is phi 2. This is minus 2. Gamma minus 2. Sorry. It's gamma minus 2. And then you're going to have the variance of zt is sigma square, right? So you have a sigma square. So now we're going to multiply the xt to this AR2. Therefore, we can have xt in terms of two series, right? Xt in terms of two series. So let's say now we multiply xt, then we're going to get multiply this equation, okay, the AR2 by xt. So you have xt multiply xt and xt minus 1, phi 2, xt and xt minus 2 plus xt and zt. So you apply the expected value. So the expected value here actually will give us the variance, okay, since the mean of the xt, e of xt basically is should be close to the value of 0, is it? So for variance, okay, so in this case you have constant, take it out, you have expected value of xt minus 1, take out the constant, xt minus 2, then you have e of xt and zt basically are not correlated. Okay? So in this way, the xt and xt have no lag difference, so this will be the variance of the covariance, sorry, which is the variance cell. Okay, then you have lag 1 here, so you have phi 1 gamma. So since the covariance actually is a even function, so therefore the minus and plus should provide a same value. So it's just like a mirror in between the leg 0. So gamma leg 1 and gamma plus 1 is the same. Okay, so this one we use gamma leg 1. So this one is gamma 2. So the variance of xt here, okay, basically if you find the variance of xt, you end up to get xzt squared, okay, which is a sigma squared. So you have a sigma squared. So let's say this is one of the equation we need afterwards. So this is for tau equal to 0 basically 1. Okay, so for tau equal to 1, we're going to put it inside the Yarn-Walker equation. Okay, so for tau equal to 1, then we just put in the Yarn-Walker equation. So you have gamma based on this one 0, 1. So this is 0, this is minus 1. Okay, so this is 1. Phi 1 gamma 0 because 1 minus 1. Okay, so this is 2 minus 1. So this is 1 minus 2, minus 1 and plus 1. Okay, so this is plus 1. And then for the equation, this should be more than 1 actually, okay? Larger than 1. Because if you're talking about the non-zero terms, so this tau must be not minus 1. So but anyway, it's also true for actually 1, okay, for this case, tau equal to 1. So this will be the equation. So if you rearrange this equation, put the gamma 1 to one side. So you're going to have gamma 1, 1 minus phi 1 equivalent to phi 1, phi 1 gamma 0. Okay. So this is 0. Okay. So your gamma 1 is nothing but phi 1 over 1 minus phi 1 gamma 0. Okay. Oh, sorry, this is 2. This is 2. 0, this is 2. This is 2. Sorry, this one is 2, gamma 2. So you bring this to the other side. So this gamma. So let's say this is basically our covariance function, okay? But we need a serial correlation function, is it? Or autocorrelation function. So do the same thing for tau equal to 2 for this one, okay? Using this equation. So tau gamma 2, this is gamma 1, gamma 0. Okay, so that will be the tau equal to 0, the 2. So you're going to have gamma 2. So phi 1 is gamma 1, phi 2 is gamma 0. So we know that the gamma 1 is what we have obtained earlier. Plus phi 2 gamma 0. So you have can take out the common item gamma 0. So you're going to have phi 1 square over plus phi 1 phi 2 gamma 0. Oh, sorry, there's no gamma. So this one is for this one is for this. So this will be the leg 2. So this will be the third one. So this will be the leg 2 gamma, isn't it? So in order to form the ACF autocorrelation function, okay, for xt, then we're going to have, let's say this is the population series now. Okay? So this is, of course, it's x here. Okay, so for tau, so we know that just now we have tau going to 0. So basically this is actually the gamma of tau over gamma the 0. Okay, so for tau going to 0 basically is this or this is always 1. Okay, this one is no need to prove. So when tau going to 1, this is what we have, isn't it, just now? This one. So this value over the gamma of 0. This whole thing divided by gamma of 0. So you cancel the gamma 0. Okay, so this one you end up to have phi 1 over 1 minus phi 2. Okay, so basically it's the coefficients of gamma 1 over 1 minus phi 1 over 1 minus. So the coefficients value. Okay? For tau equal to 2, which is this one you obtained just now. So divided by gamma 0, so the only coefficients. Okay, so this one you're going to have phi 1 square over 1 minus phi 2 plus phi 2. Okay, so how about tau larger than or equivalent to 3? So we have a general formula like using this Yao-Walker. So divide everything by gamma 0, isn't it? So divide this by gamma 0, you have rho tau. This is phi 1 rho tau minus 1, phi 2 rho tau minus 2. Okay, so instead of covariance, it become autocorrelation. Okay, so in general, you're going to have phi 1 rho tau minus 1 plus phi 2 rho tau minus 2. Okay, this is for all the rest of the values. So you can just end up to have a ACF function for AR2 in this particular. So what is this value? Basically, you substitute tau 3, 4, 5, 6, and so on, then you will get by substituting the or a recursive process to find out the coming legs of the ACF. Basically, what you get is something like this. So if your phi is 0.5, phi 2 is 0.7, let's say, sorry, this is 0.3, 0.5, then you substitute, and this values definitely will be smaller than the previous one. Okay, so you're expecting if this is your leg or your tau is 0, then you always 1. Right? So 1, then you follow this coefficient. 2, 3, and so on and so forth. Okay, in this particular way, we actually can show that the ACF for the pure autocorrelation function, okay, is always going to have a tails off gradually condition under the order of different p here. Okay? So this case p is 2. Okay? So if you're AR3, AR4, AR5, still you always get the similar pattern of under the ACF. Okay, so this is what happened for AR2. Okay, guys. So this is using the Yao-Walker to determine the ACF for AR2. Okay? So you have a gradually uh, reduction or decay of the ACF, okay? This is over time. Okay? So getting less and less and less. Less and less. Okay, guys. So this is the ACF for AR2. Analytically, this is how you derive it. Okay, guys. So see you guys in other sessions. Bye bye, guys.